All right, so next up looks like we get Jeff Diebold presenting non-integrated hot reservoir variable conductance heat pipes for lunar surface applications. Jeff, if you're ready to go, please take it away.
So my name is Jeff Diebold. I'm an R&D engineer at Advanced Cooling Technologies. I'll be talking about our work developing some hot reservoir variable conductance heat pipes. This work was all done on a Phase 2X and Phase 3 NASA SBIR program sponsored by NASA Marshall, and Jeff Farmer was our technical monitor. Colleen Giroux was the PI, and I also want to just acknowledge several of our product development engineers, Josh Smay, Tim Hahn, and Ryan Spangler, who helped out with some fabrication and design work. So just a quick background of warm reservoir VCHP. So a warm reservoir variable conductance heat pipe is an excellent device to provide tight thermal control in environments with highly variable temperature or power requirements. So in the warm reservoir VCHP, the reservoir of non-condensable gas is located close to the payload and follows the payload temperature. Then when the pipe is in its normal operating mode or full power maximum sink temperature, the vapor temperature is high and compresses the non-condensable gas, opening the entire condenser for heat transfer. As you reduce power or reduce the sink temperature, the vapor temperature drop causes a reduction in vapor pressure, which allows the non-condensable gas to expand into the condenser, blocking area for heat transfer, decreasing the overall conductance and minimizing the temperature drop of your vapor and therefore the payload. And then they are also useful for survival mode, where you have low to no power and very cold sink as the vapor condenses and contracts back into the evaporator, and the gas occupies the rest of the heat pipe, preventing unwanted heat leaks other than conduction through the envelope. So they're excellent thermal control devices, especially compared to cold reservoir VCHPs. They're great for applications such as lunar night survival. A couple of challenges that we were looking at addressing in this work were mitigating the negative effects of working fluid migrating into the reservoir of non-condensable gas, and then also reliable startup and operation in both a microgravity and gravity-aided environment. So I'll talk more about these challenges in a minute. And so then I'll also be showing the work we did to design and fabricate two separate non-integrated warm reservoir VCHPs that included hybrid wicks. One is an engineering demonstration unit for NASA's Viper, and then the other is actual flight hardware for Astrobotic's lunar lander Peregrine 1. So when we say a non-integrated reservoir versus an integrated reservoir, we're talking about how the reservoir non-condensable gas is integrated with the evaporator. So in this simple illustration, this reservoir would be considered integrated with the evaporator as it's in close contact. A non-integrated reservoir is simply separating the reservoir from the rest of the heat pipe, except for the tube that connects the NCG to the pipe. So the reason for this is because during long periods of non-operation, or when the pipe is disturbed through a physical disturbance like its tilt or shakes, it's possible to get working fluid into the reservoir. This can happen through diffusion over long periods of time, or just by, like I said, jostling the pipe can result in this. When that happens, you get an increased partial pressure of vapor within the reservoir, which then tends to displace non-condensable gas into the condenser, and blocks a portion of the condenser, increasing the thermal resistance of the pipe. So one way to get rid of the working fluid from the reservoir would be to heat the reservoir. However, when the reservoir is closely integrated to the evaporator, this is challenging because you also heat the evaporator and increase the vapor pressure of the whole system. So by just simply separating the reservoir from the evaporator of the heat pipe, or having a non-integrated reservoir, now when the pipe isn't operating, you can apply low levels of heat for short periods of time to the reservoir to essentially purge any working fluid and restore normal operation for the pipe. The second feature that we utilized here in the pipes that I'm going to be discussing was a hybrid wick. So typically in microgravity environments, grooved heat pipes are a good choice due to the high permeability of the grooves for liquid return. So the grooves provide the capillary pumping to return liquid to the evaporator. and they have high permeability, allowing power to be carried over longer distances. When the pipe then operates on the lunar or a planetary surface, you generally want to operate in a gravity-aided mode, especially if you have grooves. But this then leads to the challenge of liquid pooling in the evaporator and causing temperature spikes during startup. So in this kind of illustration here on the left, this would be for a conventional grooved pipe. The liquid will pool in the bottom of the pipe prior to startup. So when you apply heat, you have pool boiling, which can lead to higher resistance, but you can also have portions of the evaporator that aren't covered with fluid, so you can have temperature spikes. And so over here on the top right is a plot from an old test from ACT showing the startup of a grooved heat pipe, and you can see these clear temperature spikes in the evaporator. A hybrid wick combines a porous wick in the evaporator with the grooves in the adiabatic section. So this porous wick here could be either sintered powder, screen, or a variety of others. This has two benefits. It helps to improve nucleate boiling in the evaporator, and then it also helps distribute liquid throughout the evaporator to reduce or eliminate these temperature spikes. So then the plot on the bottom right shows startup of a similar pipe, but with a hybrid wick, and you can see the temperature spikes have been eliminated. So based on this, we designed and fabricated two separate non-integrated hot reservoir variable conductance heat pipes with hybrid wicks. The first was built as an engineering demonstration unit for NASA's Viper. If you're not familiar, Viper is a rover set to explore the lunar surface for a 100-day mission, and the thermal management system needs to carry heat from the warm electronics box up to the radiator panels for dissipation. So one of the options that ACT investigated was a variable conductance heat pipe. And so here you can see a CAD model of the pipe that we designed and built. This is an aluminum ammonia variable conductance heat pipe sized for about 150 watts, 1.47 meters in total length, screen wick in the evaporator, and then there weren't actually grooves. It was just a clear pipe throughout the adiabatic section. And then two additional interesting features were a bimetallic adiabatic section. So the evaporator and condenser are both aluminum, but the adiabatic section here is actually stainless steel to reduce any conduction heat leaks that would occur during survival mode when the pipe is not operating and you want to minimize heat loss to the environment. And then the second feature, interesting feature, was a flexible adiabatic section. So here we actually have nested flexible lines here for the pipe itself, for the vapor, and then also the inner line there for the non-condensable gas. And the flexible feature was incorporated to accommodate launches or launch-induced vibration between the evaporator and condenser. Here we can see a time series of temperature data across the pipe during startup. So from the ambient condition, we just applied the max power of 147 watts and monitored temperature during startup. So we can see temperature kind of grouped here. We've got the evaporator temperatures, the adiabatic and condenser temperatures, and then the non-integrated reservoir, which operates at a elevated temperature compared to the rest of the system. But looking at the very beginning of the plot, we see the temperature of the evaporator was a very smooth startup, despite the liquid pool in the evaporator due to it being oriented in the gravity-aided mode here. So the hybrid wick feature successfully prevents the formation of any temperature spikes during startup. Here we can see a plot of the temperature control capability of this variable conductance heat pipe. So starting at the left here, this would be at the steady state of 147 watts with a chiller block or set point temperature of 15 degrees C. We then began to lower the chiller block set point all the way down to minus 65 C while keeping the power to the evaporator constant. And so while decreasing the sink temperature from positive 15 to negative 65, we see only about a 30-degree drop in temperature of the evaporator or the payload. Then from there, we then stepped the power down from the maximum 147 watts all the way down to 1 watt while maintaining the chiller block set point at the negative 65 C. And so here we saw, despite decreasing the power by nearly 150 watts, the evaporator temperature only dropped about another 12 or 13 degrees there. And so despite the very low power and low sink, we still maintain an elevated evaporator temperature. Here we can see a couple of temperature distributions for this pipe. The top plot is at the design operating condition of the max power and sink temperature. So we can see the evaporator in red, adiabatic green, and blue is the condenser, while yellow represents temperatures on the reservoir. We can see a slight gradient throughout the condenser, implying that there was some non-condensable gas in the condenser, even at this maximum power and sink temperature condition. So there may need to have been some tuning or fine tuning of the NCG amount. And it's also possible some fluid had worked its way into the reservoir and displaced some non-condensable gas. Then when we go into the low power, low temperature condition, we can see now a very large temperature gradient through the adiabatic section due to the non-condensable gas blocking vapor from traveling to the condenser. From these results, we calculated maximum and minimum conductances and estimated a turndown ratio of over 540 to 1. The second pipe that we built was for Astrobotic's lunar lander Peregrine 1. So this is actually flight hardware that will be on board the lunar lander when it launches. It's going to operate as a standalone technology demonstration unit, meaning that it's not serving any payload on board. It has its own dedicated heaters to demonstrate operation of the device in microgravity and on the lunar surface. So this is also an aluminum ammonia heat pipe, again with a non-integrated reservoir. You can see the CAD model down here, the reservoir, evaporator, and adiabatic and condenser section. A unique feature here was the 3D printed evaporator. So this entire evaporator is 3D printed, including the wick. The porous wick is also 3D printed, and it interfaces with the grooved extrusion that makes up the adiabatic and condenser section. And so we can see some pictures of that here. The 3D printed aluminum heat pipe with the 3D printed wick, and then this model or this CAD model illustrating how the grooved heat pipe interfaces with the porous wick. And then in the bottom picture, we see a picture of the actual prototype. This prototype we tested, or will also include in flight, a special heater on the reservoir that is designed for this purging process I've discussed. So there's a primary heater below this plate here that is to simulate the heat load that the pipe would need to cool. But during periods of non-operation, we can apply heat to the reservoir for short periods of time to purge any working fluid from that reservoir in order to restore the nominal operating conditions. So looking at some experimental results, we started with a startup test here. So this is in the gravity-aided orientation, where again, there would be a liquid pool within the evaporator. And we can see again, no temperature spikes indicated during startup. So the profile here is very smooth, indicating that that porous wick in the evaporator helps prevent any temperature spikes. And then just as reference here, this heat pipe is carrying 40 watts. The pipe itself can carry a lot more than 40 watts, but 40 is the limit that we're allowed on the lander. Here we see a temperature control test of the Astrobotic VCHP. So again, starting at the maximum power and sink temperature conditions, and then gradually stepping down the heat sink temperature. Here we went from a chiller block set point of 40 C all the way down to, this is minus 100 C. And despite that 140 degree drop in the sink temperature, the evaporator temperature dropped less than 20 degrees, showing the effective thermal control feature of the VCHP. And then from there, we stepped the power down from 40 watts down to 1 watt, and the evaporator temperature ended at minus 37 degrees C with 1 watt applied and a sink temperature of minus 100. Here again, we can see some temperature distributions at the max power and max sink, and then at the minimum power and minimum sink. So again, similar to the previous pipe, we do in this plot, we do see a temperature gradient throughout the condenser, again indicating that the NCG needed some fine tuning here to open up more of that condenser and increasing the maximum on conductance. But then in the off mode, we can see a very large gradient through the adiabatic section, again, due to the non-condensable gas blocking the heat transfer from the vapor. The plot on the top right just shows the variation in thermal conductance as a function of sink temperature, where here we have an estimated maximum conductance of a little under 3 watts per Kelvin and a minimum of 0.015 watts per Kelvin for a turndown ratio of about 185. But again, this maximum conductance is lower than what this pipe can actually do, because we can open up this condenser a bit more with some fine tuning of the NCG, and we are only applying 40 watts, whereas this pipe, the capillary limit of this pipe was much higher than that. Then this final test here is demonstrating this purge concept. So as I said before, during periods of long periods where the pipe's not operating, a working fluid can migrate or diffuse through the non-condensable gas and then into the reservoir. When this happens, that vapor pressure, the partial pressure of vapor within the reservoir, can displace some non-condensable gas and block a portion of the condenser, increasing thermal resistance. So if we start looking at this area here, temperatures on the pipe as a function of time. Over here, what's indicated at steady state 1, this is maximum power and maximum sink temperature and a vapor temperature of 58.9 C. We then shut down power to the evaporator, applied some cooling to the condenser, and then applied 12 watts to the reservoir. So the lines here show the reservoir temperatures. As we are applying that 12 watts for roughly an hour or so, we increase the reservoir temperature to roughly 90 degrees, and then we shut off power to the reservoir and let the pipe heat up, and then apply back full power and maximum sink temperature back to the evaporator. And we can see we achieve a new steady state here where the vapor temperature is now 56.5 degrees. So we're at the same power and sink temperature conditions, but we see a reduction in vapor temperature of a little over 2 C. So this was because of this purging process, pushing some of that working fluid out of the reservoir. We then just did a second purge test, very similar to the first, shut down power to the evaporator, applied a small amount of power to the reservoir for an extended period of time, and then went back to a new steady state, and we achieved an even lower temperature of 55 C. So we can see we were able to bring the operating temperature of the pipe down nearly 5 degrees via these purging steps. So this pipe currently is installed on Astrobotic's lander and has been sitting there, not operating for several months now. So once it's actually in flight, the first step will be perform a purging process similar to what's shown here prior to operating the pipe as an actual heat pipe.
3 minutes.
All right, so just a quick summary. We designed and fabricated 2 non-integrated warm reservoir VCHPs with hybrid wicks, demonstrating their advantages for both thermal control as well as startup performance and the ability to control or at least mitigate the effects of working fluid distributions into the reservoir. These pipes were built for NASA's Viper as well as a flight hardware for Peregrine 1. And we demonstrated fairly high thermal turndown ratios of 544 to 1 for Viper and about 185 to 1, although again, that's a relatively conservative turndown ratio. And then we successfully demonstrated the effects of independently heating reservoir for purging the working fluid.